Department of Collegiate Education, Digital Learning. Welcome to the video session of VSc 3rd semester, Physics 301, Electricity and Magnetism. Chapter name is DC Circuit Analysis, presented by Savita S. So the contents are overview, Thevenin's theorem, steps involved in Thevenizing a circuit, proof of the theorem, explanation with a solved problem. So in this video, I'll be discussing about Thevenin's theorem and its application. So in most of the electrical networks are usually complex interconnection of several circuit elements with sources. So in such a scenario, determination of output current and voltage becomes difficult. Hence, a theorem was discovered by Frenchman Leon Charles Thevenin and German scientist, independently by German scientist Helmholtz, to simplify complicated networks. So this theorem is applicable to simplify complex electrical networks. So we'll see what the statement is. Statement says that any two-terminal bilateral network consisting of several fixed resistances and voltage sources can be replaced by an equivalent circuit consisting of a single voltage source of EMF VTH in series with a single resistance RTH. So, for example, if this is a complex network consisting of several resistances, source connected to an external load, then this circuit can be simplified by using a Thevenin source, a single source and a single resistance. Several resistance can be replaced by a single resistance. So the complex network can be simplified by having a single source and a single resistance called as Thevenin source and Thevenin's resistance connected to the load resistance. So in the simplified network, whatever current we are getting will be same as what we had in the complex network. So we'll see how to Thevenize a circuit. So the first step is to remove the load resistance and calculate the open circuit voltage across the output terminals. Replace all the voltage source by their internal resistance and calculate the Thevenin resistance between the output terminals. Draw the Thevenin equivalent circuit consisting of Thevenin voltage and Thevenin resistance. Connect the load RL and find the current through RL and voltage across RL. So suppose this is the network that we need to Thevenize. Then what needs to be done is first remove the load resistance. Then this becomes an open circuit. And find the Thevenin's voltage across the output terminals. So once the circuit is open, there is no current through this open-ended. So whatever current that is flowing through the resistance R2 will give rise to a voltage that is called as Thevenin's voltage. So first we have to find the Thevenin's voltage. Next, by removing the load and the source, we have to find the effective resistance of all the resistance that are present in the circuit. In the circuit we have three resistances, R1, R2 and R3. So we need to find the effective resistance by looking back at the circuit from the open end. So we'll get the Thevenin's equivalent resistance, that is RTH, and the Thevenin's voltage VTH. So RTH and VTH are now connected to the external load resistance. So this circuit, simplified circuit, is electrically similar to the complex network because it gives the same load current as that is given by the complex network. Same load current and same load voltage. So the steps are, first is to remove the load resistance, find the voltage, open circuit voltage. Then find the effective resistance by removing the load and the source by looking back at the circuit. So the effective resistance and Thevenin's voltage are now forms a part of the Thevenized circuit that is connected to the external load resistance. So we'll see how we can prove that the current is same in both the networks, in the complex network and the Thevenin network. So first we'll consider a complex network and find out what is the load current, expression for load current. So to find the expression for load current, we find the effective resistance. So the effective resistance of the circuit. In the circuit we have three resistance, R1, R2 and R3, and the load resistance. So the effective of all the resistance is, here R3 and RL are in series, and that series combination is in parallel with R2. So the parallel combination will give rise to R2, R3 plus RL into divided by R2 plus R3 plus RL. So it is like this. If R1 and R2 are in parallel, the effective resistance will be R1 R2 divided by R1 plus R2. Now these two, R3 plus RL combination is in parallel with R2. So the resistance, parallel combination resistance becomes this much. That combination is in series with R1. So plus R1 will be the effective resistance of the circuit. So main current is given by the supplied voltage divided by EMF of the battery divided by effective resistance, which is equal to V divided by, substitute for effective resistance. And if you simplify this by taking the LCM, you will get an expression for main current in terms of R1, R2, R3 and source voltage. Now to find the load current, we know what is the main current. Main current means current supplied by the battery. So that main current, when it reaches this node, gets divided into two parts. IL is the branch current which is flowing through the load resistance. So branch current IL is given by the branch current formula. Main current into resistance of the other branch divided by sum of the resistance. So there are two branches here. R2 forms one branch. R3 plus RL forms another branch. So for this main current, there are two branches, R2 and R3 plus RL. So sum of the branch resistances are R2 plus R3 plus RL. So branch current formula says that main current into resistance of the other branch, I into R2, divided by sum of the resistances will give rise to load current. So we'll substitute for main current and simplify this, then we'll get an expression for load current. Now we'll consider the Theveninized circuit, where we have a single source and a single resistance of value VTH and RTH connected to the load resistance. In this case, we'll find an expression for IL. So VTH, Thevenin's equivalent circuit with Thevenin voltage VTH and Thevenin resistance RTH is given by VTH is equal to V R2 divided by R1 plus R2. So RTH is, so for finding out VTH, we have to remove the load resistance. So if we remove the load resistance, then whatever voltage we get at the open end, that is given by V into R2 divided by, we are finding out the voltage across R2. That is the open circuit voltage for VTH. So V into R2 divided by R1 plus R2 will give you VTH, Thevenin's voltage across R2 is given by current into R2. Current is V divided by R1 plus R2 divided into R2. So RTH will get when the total effective resistance when load and source are removed. When load and source are removed, what we get is R1 is in parallel with R2, that combination is in series with R3. So R3 plus R1 R2 divided by R1 plus R2. So IL, the load current, is given by VTH divided by RTH plus RL. VTH divided by RTH plus RL. total EMF by total resistance will be the load current. Because it is all in, they're all in series, we don't need to apply branch current formula here, is equal to, substitute for VTH and substitute for RTH, and if you simplify this, you get an expression for IL, load current in the Thevenin circuit, which is similar to what we got for load expression in the complex network. So expression for load current is the same in case of complex network and also in the Thevenin network. Hence the theorem is proved. So we'll see how exactly this can be done by solving a problem, numerical problem. So here we have taken a circuit with a single source 48 volts connected to 3 resistance R1, R2, R3, 12 kilo ohm, 4 kilo ohm, 8 kilo ohm, and a load resistance equal to 5 kilo ohm. So for this complex network, we'll find out what is the main current and the load current. So main current is equal to supply voltage 48 volts divided by the effective resistance. So the effective resistance is 8 plus 5 are in series, that is in parallel with 4K. 8 plus 5 is 13. 13 is in parallel with 4. That entire combination is in series with 12 kilo ohm. So that comes out to be 15.06 kilo ohm. So 48 by 15.06 kilo ohm is equal to 3.2 milliamps is the main current. So load current means branch current formula will have to apply, is equal to main current into resistance of the other branch divided by sum of the resistances. So main current into resistance of the other branch. We want load current, so we'll take the resistance of the other branch. There are two branches here. One is 4K and another is 13K. So we'll take the resistance of the other branch 4K divided by sum of the resistance. 4K plus 13K is 17K, which is equal to 0.75 milliamps. So load current is 0.75 milliamps. So this is the load current in a complex network. Now we'll simplify the network and find what is the load current. We'll see whether both are matching or not. So to Thevenin, what we have to do is remove the load resistance, find the open circuit voltage. So when we remove the load resistance, this becomes open circuit, no current flows through 8 kilo ohm. So the total resistance is 12 plus 4, 16, and source voltage is 48 volts. So main current is always given by formula EMF divided by total resistance. EMF is 48 volts. Total resistance now is 12 plus 4, 16, because there is no current flowing through 8 kilo ohm, so we cannot take that into consideration. So 12 plus 4 is 16. 48 by 16 is 3 milliamps. So voltage across 4 kilo ohm is the open circuit voltage. So the open circuit voltage is called as Thevenin's voltage, which is equal to main current into 4 kilo ohm, which is equal to 12 volts. So now we have to find the effective Thevenin's resistance. To find the Thevenin's resistance, remove the load, remove the source, and replace the source by its internal resistance. Here, if the internal resistance is very small, we can neglect it. So the total effective resistance is, when we look at the circuit from the open end, what we can see is 12 and 4 are in parallel. That combination is in series with 8 kilo ohm. So 4 and 12 are parallel in series with 8 kilo ohm. That comes out to be 11 kilo ohm. So now we will have a Thevenin circuit having Thevenin's voltage 12 volts as the source and Thevenin's resistance 11K as the RTH. So now connect the load back to its position and find the load current. Load current is now given by 12 volts is the EMF divided by total resistance. Total resistance is 11 plus 5, 16K is equal to 0.75 milliamps. So in the Thevenin circuit, whatever current we are getting is the same as the complex network current. That means these two circuits, the complex network is electrically similar to Thevenin circuit. So hence Thevenin's theorem, using Thevenin's theorem, we have simplified the circuit and we can easily find the load current. So these are some of the references that students can refer to for this Thevenin's theorem for better understanding of the topic. Thank you.